So you'll get a quick, should get a quick little note right now saying recording in progress. Just say okay if you would, please. And let me hop really quick in this PowerPoint, and I'll try to finish quickly, but ask questions along the way. I kind of oversimplified it in a lot of ways, but at the same time, oops, get to the right slide to start with. I just want to talk a little bit about supermassive black holes, particularly like the kind like Gargantua in the movie. They're kind of interesting. Again, just a quick reminder, a quick review. What do we define the edge of a black hole? We define it as the event horizon. That's the point where the gravitational field is so intense that the escape velocity is equal to or exceeds the speed of light. There is no limit to the volume that a black hole can occupy. Unlike other things that have definite limits, black holes can get as massive as you would like. There's no upper bound on this one. Lower bound, as you get smaller and smaller, they evaporate very quickly. But yeah, upper bound, no limit at all. Real quick, the masses of black holes are usually given in terms of solar masses. Oh, yeah, go ahead, Jerry.
Isn't there this concept of Planck mass, which is like the lowest possible mass for a black hole, because at that point it will just be one Planck unit?
Yep. So technically you're right. The smallest possible, since mass and energy are quantized, the smallest possible mass, you're right, technically is 1 Planck unit, about 10 to the minus 32 kilograms, give or take a bit, is the smallest chunk of mass you can physically have, or smallest chunk of energy you can possibly have. Don't quote me on that exact number. I keep thinking, am I doing joules or kilograms? That's joules. Never mind. I'll fix that later.
Did search, and it's 2.18 times 10 to the power of -8 kilograms.
What? Okay, yeah, okay. Thank you. Sorry, taking the Planck constant in terms of energy, which is 10 to the minus 34, divided by c squared. Yeah, okay, yeah, it makes about right sense. The speed of light's a finite value, which is part of the issue here. Interesting enough, black holes actually shoot out matter usually along 2 jets that move nearly at the speed of light. This is M87. We'll get to see that one again in just a moment. But real quick reminder of a little bit of the math. Escape velocity, just using energy conservation, is equal to 2 gm over r, where r is how far you're away from the center of mass. And if you set the escape velocity equal to c and then resolve this for a radius, you get this. Warning, this is only valid for a non-rotating black hole. And so I'm going through this a little bit fast, but don't panic. Where g is the universal gravitational constant, 6.67 times 10 to the negative 11. M is the mass of the black hole. C is the speed of light. You square it, gives you the Schwarzschild radius, or Schwarzschild's radius, which is the radius of a non-rotating black hole. Where we're talking about the radius, that's the point of no return. This is where the escape velocity is equal to c, and inside this point, it's greater than the speed of light, and there's no way to get out. Even if you converted all of your mass into energy, you wouldn't have enough energy to escape once you cross the event horizon. Your deficit in gravitational potential exceeds the total energy you have. And it all really comes down to a matter of density. Remember, rho is used for density, in this case, mass per unit volume. We also use rho for charge per unit volume and a few things. But if you take the mass of a black hole divided by its volume, 4/3 pi r squared, or r cubed, plugging in this for r, you'll discover the density of a black hole is given by this. You're like, ooh, Miss Clommer, that's not very pretty. Well, there is something interesting in here. The density of a black hole, all of these are constants except for the mass of the black hole. So as the mass of a black hole increases, the density of the area enclosed by the event horizon gets smaller and smaller, to the point where supermassive black holes, their overall density, if you incorporate all the way out to that point, actually can be equal to that of water, which is one of your questions tonight. And actually, if you use this equation, you can actually solve it real quick, because you know the density of water. You can figure out what the mass required is, so that the average density of the event horizon and the rest of the volume then would be equal to that. It's interesting, actually. Why is that kind of relevant? It's relevant because of the fact, and there's one slide I didn't put in here. Yeah, just a real quick warning. So I'll come back to the thought I had. gravity warped space-time. This model here, it should be really warping into the bulk, which we talked about before. This model is pretty, but it really is deceptive because you think that they just have a two-dimensional opening over here. In reality, it's a spherical opening, and the bend is into another dimension. And you could say time, or you can also say it goes into the bulk, depending on if you think there's higher dimensionality. One of the cool things about black holes is it's the no-hair theorem. There are only three properties of black holes that you can measure: their mass, the charge with an asterisk by it, I'll talk about that one, and angular momentum are the only properties a black hole can possess. Doesn't matter what mass fell inside to make it. It could have been a gas, it could have been other stars, it could have been that. But the only things we can measure from the outside are these three quantities. Why is it called the no-hair theorem? If you've got twins, one way of telling twins apart is you look at their hairstyles. Usually twins don't do the same hairstyle. So this is called the no-hair theorem. If you had two black holes with the same mass, the same charge, and the same angular momentum, you could not tell them apart. There would be no physical way to distinguish them except their position in space. Every other quantity, like what went into them to make them, is completely hidden from our part of the universe. So indistinguishable. Normal sized black holes are usually in the range of 3 to 10 solar masses. You can also have microscopic primordial size ones, size of atoms, and then supermassive black holes in the order of millions to billions of solar masses. Yeah, keep asking questions. I'm going through this fast. Yeah, this is the one. You recognize it. Very good. This image right here is the first image of the black hole in the middle of our galaxy. It was released officially about 24 hours ago. And so I just couldn't resist sticking it in here because it's so brand new. The black hole at the center of our galaxy is about 4.6 million solar masses. And yeah, it literally is, if you look at the news, it was imaged, literally 24 hours ago was the press conference. I just couldn't resist it. I like it. It was actually much harder to image than the one that they did release a few months ago, where they imaged another distant galaxy. This one is much, much smaller. You're like, smaller? 4.6 million solar masses is small? Yeah, it is much smaller in angular displacement than the one at M87, which is literally billions of solar masses. So our black hole is small compared to that. So it was harder for them to image this one, even though it's closer. Most black holes are believed to come from the death of stars. Blue stars, very heavy stars, have shorter lifetimes. They convert to black holes much sooner. If they're blue, they're also very massive, which is why I have this picture of blue ones. Real quick, stellar evolution, since I mentioned it real quick. Star has to have a mass greater than about the 10th of the mass of our sun. Oh, sorry, I'm using a new symbol here. Instead of talking a mass of the sun, this symbol here is the symbol used for one solar mass. You're like, what? Yeah, I love it. This is actually the archaic symbol for sun in Chinese, and it is actually the variable or character we use, m sub that, for the mass of our sun. For more, so once you get above that mass, you get ignition, fusion begins. And if the star is massive enough, it will actually start fusing other elements. Helium into beryllium, beryllium into carbon, carbon into oxygen and nitrogen. Eventually, you end up with some more interesting ones. You got hydrogen fusion going on, you got helium, you've got carbon, you've got silicon, magnesium, neon, oxygen. But the moment it does this, the moment it starts making iron, iron is a problem. It turns out, just a quick reminder, and most of you know this already, if you take any element on the periodic table smaller than iron and you fuse it together, it releases energy. And anything on the periodic table that's heavier than iron, if you fission it, take it apart, it releases energy. But iron is actually the most stable nuclei. What happens when the star tries to fuse iron? bad things happen. And that's why it's called ash in this diagram. You literally, it cannot go any higher than iron. If it tries to do that, and this is what actually causes the death of a star, the moment it tries to fuse iron into a heavier element, instead of releasing energy, it absorbs energy. And please remember, the only thing keeping a star up is the incredible temperature generated by the fusion at the center, which is creating pressure to hold the outsides out. The moment it fuses iron in the center, the inside begins to implode. And then the rest of this material, which has been held up by this pressure the whole time, starts moving inward and will approach the speed of light. The collision when it all meets at the center is what causes supernovas. And then that does fuse heavier elements. And that's really exciting. That's actually where most of our heavy elements come from. So if you've got iron and the star's mass is greater than that of 1.4 solar masses, the star will become a supernova or type 2 supernova, the one I just talked about. If it's less than that, it actually becomes what's called a white dwarf. A white dwarf, you get matter pressed all together in the nucleus. The electron orbitals get pressed in, so they're right up against the nucleus. And at that point, it stops. Where does this 1.44 come from? It's called the I always mispronounce this. Never mind. You can see it. I even practiced this before I got here today. Yeah, thank you. Thank you. Chandrasekhar limit. And it simply expresses the idea that at some point the degenerate electrons, which are no longer in standard orbitals, will exert a pressure saying, I can't go any tighter than this. And it exerts a force backwards. And you can use this equation to discover, okay, the mass is about 1.44 times the mass of our sun. Beyond that, the degenerate pressure is not sufficient. And what do you end up with? Then you end up with either black holes or neutron stars. Now, here is the big argument. I need to explain this one real quick. Then the amount of mass required is actually a bit of an argument. And I should have done a little bit more research to see what currently is on. I didn't get a chance to read enough papers on this one. These numbers are somewhat flexible. No one's really quite sure how much it takes to make a neutron star. We know it's greater than the Chandrasekhar limit, but that 3 number here could be 5, it could be 6, it could be 8. I've read different papers, and I need to find out where the current thought is on this one. Jerry, have you read recently? I didn't get a chance to research.
If I remember correctly, the 3 is referring to the star's core mass.
Yeah. So all the mass was being thrown out. But even there's an check on that one. So there's a bunch of unknowns in this one. The mathematics here are not nearly as clean cut as it is for the white dwarf. But Jerry, you can keep Googling it and see if you can find. I know that's the residual core mass after the outer layers are thrown off. So for example, our sun, when it starts fusing helium, will go through a bubble point where most of its gas will actually bubble off. It inflates. That's when it swallows the Earth. During that point, it's going to lose most of its mass. And so the core mass, when it's done, of course, it's going to be much, much less than the 1.44 Chandrasekhar limit, but it's going to become a white dwarf. Whereas stars, even after they blow off their outer layers, if their core masses are somewhere, we think greater than the Chandrasekhar, I mispronounced it again, limit, but less than some magic number will become neutron stars. If they're more than that, black hole. Where could supermassive black holes, the ones I'm interested in? The only places we know where there could be enough mass is the center of massive galaxies. So far, we've never seen one anywhere else. Does it mean that they're not there? The answer is, yeah. The only way we can see a black hole is if something falls into it. Otherwise, remember, they are not a source of radiation. We can detect them if we can see, some optical bending, some curvature of space-time, looking at things behind them. But so far, we've not seen that anywhere outside of a galaxy. So we don't think they're anywhere else. Quasars are one way we've actually sort of determined that one. Quasars actually stand for quasi-stellar radio sources, or quasars for that. We found these things definitely could not be stars because they're so far away, but they're always seem to be at the center, at the very bright center of some distant galaxies. And so we think all quasars, all quasi-stellar radio sources are actually supermassive black holes. Another more common and more modern way of discussing these things is instead of calling them quasars, we simply call these kind of galaxies active, or galaxies with active galactic nuclei, AGNs. Interesting enough, these particular things are actually some of the brightest things in our universe. Quasars are some very distant active galactic nuclei, and the light from those actually exceeds the entire radiation from all the rest of the galaxy combined. They are only seen in the oldest part of our universe, if we look very distant. Why? Most of the time, these supermassive black holes swallow the stars that are nearby them. Once they've swallowed that, the rest of the galaxy, remember, just stays in orbit around it. They exert gravitational force, which keeps the rest of the galaxy in orbit, but they don't actually suck things in. Again, just a quick reminder, if our sun became a black hole, the Earth would continue to just quite orbit around it like it was before, because it would still exert the same gravitational force as it did before. Black holes don't suck things in, things have to fall into them. Why are supermassive black holes so interesting? I should actually talk about it. Supermassive black holes like Gargantua in the movie have some nice effects. If you're near a very small black hole, say one solar mass black hole or a couple solar mass black hole, and you're moving close to it, your feet are much closer than your head. And so you end up with this much larger gravitational force on your feet than your head, and you end up spaghettifying. Become like a piece of spaghetti where you get pulled thinly. It's actually called spaghettification. And that's because of the difference in the force of gravity between your feet and your head. That is not true for supermassive black holes like Gargantua was in the movie. In that, it's so massive and its event horizon is so far away from it that the difference in the gravitational force between your feet and your head as you cross the event horizon for a supermassive black hole doesn't necessarily have to rip you apart. And so you can actually cross the event horizon without dying. Now, in the movie, they did that, of course, but normally black holes usually have this very large accretion disk happening around it. And that accretion disk is usually heated to millions of degrees Kelvin. You'd be vaporized by the heat long before you got spaghettified. In this particular case, Gargantuan, they eliminated most of the infalling matter. So it was a quiet one. And also, the other thing, I forgot to put in the presentation, dang it, is most other ones have, actually it's in the book reading a little bit, have a photon sphere, or it's sometimes called the ring of fire. For rotating black holes, it's not exactly spherical, where light actually orbits the gravitational attraction of this. So you get that. This photon sphere or ring of fire also would tend to vaporize most material that would go through it. So you'd be vaporized into ions long before you got to the event horizon. So in the movie, they kind of took care of that, both of those features. They made sure that Gargantuan basically had eaten its breakfast already and now was just sitting around waiting for things to fall into it. Also didn't have any jets coming off of these jets, which have matter moving 99.99999% of the speed of light, are incredibly deadly if you get anywhere nearby them. The radiation is just intense. All right. So how did supermassive black holes come about? Oh, sorry, pause. One last thing on this one. So roughly how big would a black hole need to be so you could cross the event horizon without being spaghettified? The answer is it's about 300 solar masses. And I should have actually mentioned that real quick. So 300 times the mass of our sun. If a black hole is that big, it means it, by the way, they would fall into the supermassive one. No star has that much mass on its own. So the only black holes you could cross the event horizon are probably at the center of galaxies, where the supermassive ones reside. So how they come about? There's a couple of ideas. One is from lumps in the early expansion of the universe. The other one is stellar seed, where you've got a bunch of stars, or a collapse of a star cluster. And I just want to quickly mention that one. Yeah, in the Big Bang, it was extremely dense to the point where its density actually exceeded that of black holes. But then there was this hyperinflation that prevented black holes from forming. But just as hyperinflation ended, there may have been some lumps or some places where the density was larger that would cause some black holes to exist even outside of galaxies. And that could explain a few things, like, for example, there are pockets of interstellar gas that become galaxies. They could be being attracted by interstellar black holes that are not the center of galaxies. The stellar seed model, if you've got a lot of galaxies here, or a lot of stars very close to each other, say, for example, in the middle of a galaxy, it's so rich in matter that you could just have one star producing a supernova that would then seed a whole bunch of interesting other black holes forming, and then those combining to form a much larger one. I don't like this model necessarily, but it's interesting. And then finally, the collapse of a whole cluster. Oftentimes in the younger universe, you have bunches of stars that are incredibly close to each other. And if you've got black holes nearby each other that are in orbit around each other, you've got some binary star systems. You could very quickly swallow up the neighboring stars, especially in very dense star clusters like this. This is NGC 1850. And you can sort of see it's fairly dense in there. Some characteristics of active galactic nuclei: super bright. Here's a picture of it. Its luminosity of just this one thing is 5 times 10 to the 12th times the luminosity of our sun. That's a trillion times larger than the brightness of our sun. That is a lot of stars, or equivalent to a lot of stars. That is brighter than our entire Milky Way galaxy. That's just one object, one thing. They do produce usually optical jets. I told you about the matter being shot out. I didn't actually do, that's another slide I should have done. Just actually show you how those jets form. They do create crazy tidal forces on the stars around them, and those tidal forces slow down the stars in orbit around them, and then they do cannibalize the material that is in orbit around them. Tidal forces will slow down the orbit, transfer some of the angular momentum to the black hole, and that will actually allow stuff to fall in, and it's the stuff falling in that makes them so incredibly bright. Optical jets, why do they happen? The magnetic fields are usually crazy strong, and they'll actually produce, in this case, this is Cygnus X1, one of the most famous cases, and this is in the radio spectrum. You can see these clouds of gas actually being excited by the jets coming from Cygnus X1. Cygnus X1, the name for it, Cygnus is in the Swan constellation. Cygnus is the Swan, and it's X1, it's X-ray source number 1 found in the Cygnus constellation. It was our first candidate for something as unusual as out there. And tidal forces, really quick on this one. The tidal forces, the stuff that spaghettify you, directly proportional to the mass, but inversely proportional to r cubed, your distance away from it. So for supermassive black holes, this grows linearly, but this grows as the cube. And so for supermassive black holes, the tidal forces get much, much larger the more massive they are. But this one's a computer simulation of a black hole eating a sun, and it's not a really good one. Here's the sun to begin with, then it gets ripped apart a little. No, this is actually a bad one. I need to get a better one on this one. But as it gets ripped apart, it gets pulled into an arc, and as it falls in, it makes the black hole get incredibly bright. That star, as it falls through, produces what's a nice gamma ray burst. Very, very high energy as it's superheated, as it belts across the event horizon. Apparently, quasars, or active galactic nuclei, are only active for about 100 million years. Why? After that point, it's still it's absorbed all the stars nearby it, all the tidal forces it can do. So basically, you end up with a supermassive black hole surrounded by a big empty space around it. It swallowed everything that's very close, and then all the other stars are in orbit somewhere distant away from it. And at that point, it becomes quiet. It's still there. It's just no longer, not much is falling into it. Yeah, there's still tidal forces acting on these, but it's going to take a long time for them to fall in. And so only occasionally does it pull in a new star. Some proof for this one. We actually think that dead supermassive black stars can be revived. And so if you look at elliptical galaxies, those are produced when you have two different galaxies that have collided. So these were moving in opposite directions. I don't know. This is either slightly before or after the collision. I actually don't know this image. And all of a sudden, their galactic centers both became active again. Why? As the galaxies passed through each other, the supermassive black holes suddenly got fed again as stars got close to them. And so this collision galaxies between these two, their galactic nuclei have gone active again. How do we observe supermassive black holes? Radio telescopes, X-ray observatories, optical observations, and then radio imaging by the Event Horizon Telescope that produced that image we talked about at the beginning here. Here's a picture from Hubble. You actually don't get to see, so we think this is the event horizon, we think this is the accretion disk, but even that is pretty amazing actually in the optical range. This is from a distant galaxy, but we can image it just barely enough to catch that. And then this is from the Event Horizon Telescope. The blue dots here represent the radio telescopes on the planet. We combine the signals from all of these to form these images. This is M81. This is its image and radio telescope. This is the Event Horizon, and this is the accretion disk. Although we're looking at a little bit from the edge on. You remember from the movie how you could see the accretion disk, and then you can actually, the part of it behind it was bent upward. This is probably the bent upward part right here that we're seeing around the edges. And then this is the one that was just released days ago. This is our accretion disk in the middle of our galaxy. And honestly, this one is a little suspect. It's actually a combination of a bunch of different images that they produced in the computer. And then they only included the stuff that was common in all the images, and they discarded the other parts. And so these little bright spots here may or may not be real. This is this is actually when AI attempts to do image reconstruction. Sorry, go ahead. I should explain. Yeah, it looks like a fidget spinner. You're right. But don't take this one too seriously. This one's actually pretty solid. This one, they had decent enough images. This one, they had to do a lot of software manipulation to get this, and they let the computer make some decisions on it. And that is always a little troubling. So I'm not sure how realistic that fidget spinner is. All right. Fate of the universe. Most of you know that Hawking's radiation. At the event horizon, we talked before about virtual particles popping in and out of existence. It's a little bit more detailed than that, but black holes do slowly evaporate. They produce particles at their outside edges. But I just want to give you a quick feel on this one. The evaporation time of a black hole is roughly given by this equation. So for a 1 solar mass black hole, I forgot to put the little thingy in there. Dang it, pretend I did. Its lifetime is that, which is that much longer than the present age of our universe. And to make things worse, and it's probably Jerry's question as well, it turns out tiny black holes evaporate at a much faster rate. They have a higher temperature, higher entropy. They lose it faster. And supermassive black holes are actually colder than the universe. Their temperature is less than 3 Kelvin, which means they actually don't evaporate at all. They actually absorb energy faster from remember our background temperature, our universe is about 3 Kelvin. They actually absorb energy faster from the surrounding universe than they're losing it. And so they're actually not evaporating. They're actually getting larger just bound the background radiation. Let me see what the question was. It probably was that. Do you think the future? Oh, yeah. Oh, do you think we can actually detect Hawking's radiation? To do it, we need a very tiny black hole. So maybe as our detectors get better and better, right now we can only see supermassive ones, like at the center of galaxies. if we can find a stellar mass black hole, we should be able to see Hawking radiation. But here's the issue. Sorry, I'm going to hit the math here real quick. And I'm going to use a different term here. Oh my goodness, I just wrote this out and I'm laughing now about it. Oh my goodness, that's a 5. And this is Earth masses, not stellar masses. Any black hole whose mass is less than or equal to, oh, sorry, let me reverse this, the other one here. Any stellar mass that is greater than or equal to that, its temperature is less than 3 Kelvin. So the only black holes which are radiating more than they're absorbing are ones that are incredibly small. Their mass has to be less than, oh, I've got one too many zeros in there. It has to be less than 7.5% of the mass of the Earth for them to emit more radiation than they absorb. Finding a black hole like that would be considered a microscopic black hole. Is, first of all, those should be incredibly rare. Remember, I told you need to have a star whose core is at least 3 solar masses to produce a black hole. And so to find something that has, sorry, it should be percent, 7.5% of the mass of the Earth, that's small enough where it's actually producing more Hawking radiation than it's absorbing. And those would be the only ones that would appear to be luminous without an accretion disk of stuff falling into it. Sorry, I just hit you with more math than I intended. My apologies. But keep throwing questions out there because they're actually interesting. 7.5% of the Earth's mass. That is ridiculously improbable. Unless there's microscopic black holes left over from the beginning of the universe. Hold on. Now you got me going. I got to do this real quick. So would they still be around? If you had a black hole which had that much mass, if you plug it in this equation, would it still be around? Sorry, give me just a brief moment. It would be. Okay, never mind. Yeah. There's a high probability it would still be around. So if microscopic black holes were formed when the universe was formed and they're just floating around in space, those would be emitting more radiation than the background, but just barely. Their temperature would be basically at 4 Kelvin, which would be colder than most parts of space. Yeah, it'd be really hard to detect. So sorry, answering the question. And that is, it's everybody. And I'm going to stop the share at this. Actually, I won't stop the share yet. Let me quick go to the assignment sheet. Any last minute questions before we get going on this? I'll stop the, I went to the wrong one. Doggone it. There we are. Just a quick reminder then, next Tuesday we'll meet just briefly. Just check in, see how you're doing. I'm going to ask you about your presentations and how you're doing. Homework, just answering these 2 questions about supermassive black holes. You'll find some in the reading here on Interstellar, the things that they changed about Gargantua. In fact, I think there's one whole chapter about Gargantua. And then presentations next week, Thursday, these 4, I just want to get this in the video. The rubric is here, and I'll put the weighting there as well. So there will be no homework next Tuesday night. It says to be determined. It's going to be a work time just to wrap up your presentations. And then the following 4 presentations will be during that morning time on the following Thursday. I just haven't updated the times and the people. I didn't get a chance to copy those over before class started today. My apologies. I didn't quite get there. I'll update that as soon as we get done today. All right. With that, I'm going to stop the share and I'll stop the recording. And then, are there white holes? Yeah, good. Thank you. So this actually goes back to, and I'll just answer this real quick before I stop the recording. I think I told you before that I've got a case of wine riding on the fact whether or not antimatter will float up or float down. That actually has to do with the white hole problem. So physicists always assume that all physics equations are time reversible. that if you ran time backwards, a black hole, which normally sucks in matter, should then shoot out matter, a white hole. But if I'm right, and I'm going to win the case of wine, I'm pretty sure, I think gravitation is non-time reversible. That even if you ran time backwards, things would still fall into black holes. And if that's true, there should be no white holes. There should be no opposite end to a black hole or time reversible black hole, which would actually produce matter. But I might be wrong. I was wrong about, I told you I lost a bottle of wine for, what was the other thing I bet on? And I told you, I think I told you just a while back that I was wrong. But yeah, I think I'm right about gravity and time non-reversibility. With that, let me stop the recording real quick and let's see what's in the chat. Oh, good. Oh, that was it. Okay. With that, I'm going to stop the recording and I'll say goodbye to everybody.